Let's go ahead and record. Okay, this week's lab, we're going to be looking at, last week's lab, we looked at simply torques and found some masses of symmetric objects. Now we're going to deal with rolling motion with and without slipping. Okay, and before we get there, I want to take a look at a simulation. If I remember right. Why is this not working? Oh. If you remember right, for a rolling object, I came up, we have the expression for I equal to, for any rolling object, I is equal to alpha mr squared.
Share the screen.
Okay. Share screen. Yes, thank you. For any object, we had I equals alpha mr squared. And I wrote that, for instance, its velocity was equal to the square root of 2gh over I plus alpha for an object rolling down a inclined plane. Here's its initial potential energy, and here's its velocity at the bottom. So in the case of this simulation, where I'm going to hit reset here, I've got a spherical shell. I equal to 2/3 mr squared. I've got a solid sphere where I equals 2/5 mr squared. I've got a cylindrical shell where I was equal to mr squared, and I have a solid cylinder where I equals 1/2 mr squared. Okay, look what this means. This, in this expression of alpha mr squared, alpha is equal to 2/3, alpha equals 2/5, alpha equals 1, and alpha equals 1/2. So now that we've determined this, when I hit run here, which one of these objects is going to reach the bottom first?
Hold on. I think the, oh no, wait, oh. 2/5. I'm trying to calculate, see which one's in the, I think the 2/3 one, 0.6.
Okay, which has the
Oh, that's right, no, the half.
smallest
Or-
value for alpha?
I think the 2/5.
So this is 0.4, this is 0.5, and this is approximately 0.67. And this is
Okay.
1.
1.
So the order they should reach the bottom, this will have the highest velocity, which makes me believe it'll reach the bottom first also. Then this one, then this one, then this one. So we should go solid sphere, solid cylinder, spherical shell, and cylindrical shell.
You know what? I would think that the 1 would have the would be quicker down.
The one would be quick, but it's going to have a slower velocity down. Look what that alpha is. I equals alpha mr squared. The higher the moment of inertia, the harder it is to get it rolling. These all have, so if it's harder to get rolling and they're rolling without slipping,
Right.
and it's harder to get rolling, the one that's harder to get rolling is going to get down there last.
Right.
Okay. So if we run this, and I'm going to pause it just when the first hits the bottom. So this hasn't quite hit the bottom. Here's my solid sphere. A close second is my solid cylinder, 0.5. Then we have the spherical shell. Then we have the cylindrical shell. Okay. Now, this is harder to get moving. Look at what you also have. They all start with the same potential energy. At this time, the solid sphere is going to have the greatest kinetic energy. At this time, not at all time, this is going to have the next greatest kinetic energy. Then this is going to have a little bit lower kinetic energy, and this is going to have the lowest kinetic energy. They all have the same total mechanical energy at this point. Still, now at some time later where they're all have hit the bottom, and let's pretend they're not stopped and still rolling along. Okay, they all have the same kinetic energy. But now that it's had a chance to get that extra potential energy into rotational kinetic energy, this will still be moving with a slower velocity. It'll have a lower translational kinetic energy, but a higher rotational kinetic energy. Because now its I is bigger. Its omega is going to be smaller, but I is bigger. And it also goes as R squared. We have distributed mass far out. So it'll have lower translational kinetic energy, but higher rotational kinetic energy. Okay? Because all that mass is distributed out here at the edges. Now, we said here, energy, we just learned, has to go into rotation. These are all rolling without slipping. Suppose I put a cube on a sheet of ice and it's frictionless. Now, which one of these is going to hit the bottom first?
Like the solid sphere and the frictionless cube.
The frictionless cube will hit before the solid sphere. No energy goes into rotation. It all goes into translation. And you can see it clearly hit the bottom first because it all goes into translation. Nothing's going into rotation. Okay, so now let's go to the lab because it is forcing you to go an extra step on here. We are going to do rolling motion with and without slipping. So we're going to look at motion with slipping of a round object. Okay, now remember our background equations. V center mass is equal to R omega is a condition for rolling without slipping. Okay, if your tires are spinning, like let's say you start on a wet surface or an icy surface and you hit your gas pedal, your tires slip. They're slipping. So now V doesn't equal omega R. They have a bunch of omega and you have no forward velocity. Similarly, I can have forward velocity of an object without spinning. Okay, if you've ever been bowling, you toss your bowling ball down the lane. It doesn't start rolling right away. It has forward velocity without rolling. So I can have forward velocity without rolling. Okay, imagine I take this area is going to be frictionless.
Can't see what you're drawing.
That area is going to be frictionless. So all this is frictionless and this has friction. And I launch a ball with some velocity V forward. Now, since this is, let me write out frictionless a little bit better. Frictionless. Since this is frictionless, there's nothing to cause this, give any torque, to cause this to start rolling. Then it hits this friction surface and we start getting some rolling. And then we have some rolling with some slipping. And sometime later, we get rolling without slipping. Okay, now we can calculate what that distance is based on the friction of the surface. And that's what we're going to do in our lab. We're going to find out when this is conditioned. So only when we fit rolling without slipping, this condition is met. V center mass equals R omega. Okay, so if I hit this frictionless surface, it's going to start slowing down the V center mass. Energy is going to go into rotation. Okay, that energy is going to go into rotation and we're going to get more and more rolling and rolling until we hit the point where we hit rolling without slipping. Well, we have rolling without slipping, we have kinetic friction. Once we hit rolling with slipping, we're in the case without slipping. Rolling with slipping, we'll have kinetic friction. Rolling without slipping, everything is static friction because the very bottom is at zero velocity. V center mass is going one way, the bottom is going the other way. Remember what rolling without slipping ends up showing us. Rolling without slipping. We have V center mass. The very bottom of it, relative to this reference frame, this is going with omega, V of point, we call this point P, of point P relative to the center mass equals 0. Or actually equals minus V center mass. And so V of P relative to the ground, which is equal to V of P relative to the center mass plus V of the center mass relative to the ground is equal to minus V center mass plus V center mass, which is equal to 0. So the point P relative to the ground right here is 0. The point P2 up here, V of P2 relative to the ground, which is equal to the velocity of point 2 relative to the center mass, plus the velocity of the center mass relative to the ground, is equal to, well, up here, rotation is this way still. We still have the same rotation. It is going to equal to the center mass plus the center mass, which is equal to 2v center mass. Okay, so there's one at the point at the top relative to the ground is going twice the velocity of the center mass. The velocity of the bottom is going to be going at 0 relative to the ground, and the v center mass is going to be moving at v center mass. This is your condition of rolling without slipping. This has 0 velocity relative to the ground for an instant, and so it's static friction for, so the point on the ground has static friction, which is why we get to use static friction when dealing with a car going around a curve. It's really static friction. As soon as you get slipping, you're into the realm of kinetic friction. But before you have slipping, you haven't locked up your tires, you're not spinning your tires, nothing is slipping, you're in static friction because the point relative to the ground isn't moving. That's what we were warning before with going around a curve. So what we're going to do is this V center mass is going to get slowed down, and the rotation is going to speed up. We're going to put kinetic energy translation into kinetic energy rotation. Okay, the torque is going to be the force of friction, sometimes kinetic, sometimes static, the force of friction times the radius. Okay, R cross F, and that equals I alpha. A rotational kinetic energy, remember, is I 1/2 I omega squared, and the translational kinetic energy is 1/2 mv center mass squared. We're going to go ahead and open our simulation here. And make this a little bit bigger here. And I'll make it a little bit smaller now. Okay. Let me make it a little bit bigger. So, what are our variables? We can choose a solid cylinder, a solid sphere, a thin cylindrical shell, a thin spherical shell, or a user-defined moment of inertia. In which case, we get to fill in that value alpha. Notice this is I equals alpha mr squared. We're only dealing with what this value of alpha is here. So we can put in a user-defined moment of inertia. Now let's look at a solid cylinder. Remember, a solid cylinder is 1/2 mr squared. Now, we're going to look. Here's our mass. We can change the mass. Okay. We can change the coefficient of friction. We can change the radius. And we can change the initial velocity. Now let's just look at an example here, because we're going to look at this whole thing from an example perspective. Here's an initial velocity of 5 meters per second, a coefficient of friction of 0.15, a radius of 1, and a mass of 0.5. And I hit run. Now I'm gonna pause it. My slipping distance is 4.724 meters. That's the time it takes to get rolling. That's the amount of distance it takes to get rolling without slipping. My initial kinetic energy was 62.5 joules. My final translational kinetic energy is 27.78 joules. And my final rotational kinetic energy was 13.89 joules and recreated 20.833 joules. Okay.
I don't get what the slipping distance is. It didn't look like it was spinning, before it started. Or is that what that means?
Yes. If I do run again, reset. Now, see how it's just sliding?
Oh, I see. Okay, I didn't notice that at first. Okay.
Okay, so it's sliding. It's getting up, it's building up a little bit of spinning. And what we're doing is we're watching this point. So let me reset again. We're watching this point down here. Okay, this point, that, and we're watching that the whole way. So it takes, we're starting to get some spinning actually instantly. We're instantly starting to get some spinning, but it builds up slowly because we've got a torque. The torque rate is alpha, I alpha. So there's a torque here that gives rise to I alpha. Okay. We hit run again. You see, so if we've got an alpha, if we have an alpha in there, the angular velocity is going to keep increasing until we get rolling without slipping, in which case, at that point, we will no longer get an increasing omega. So we've got a variable force here happening, we have variable torque that happens. As long as we have kinetic friction, we have a fixed torque. But as soon as that bottom comes to a stop, as soon as we hit rolling without slipping, our torque changes. And our net torque becomes 0. The net torque on the system becomes 0. And we're in the case of static friction, rolling without slipping. Okay, so until that, we have kinetic friction. Okay, and that leads to the letting it start rolling. If this was ice the whole way, it would never start rolling because there's nothing to impart angular momentum. We can't get any angular energy or angular momentum without a torque. If there's no force, there's no torque. And if there's no friction, there's no force at a right angle. There's no component of force perpendicular to the axis of rotation. So again, over here, we start out, we've got a force going, our force is trying to impede motion. So there's a force going this way. That creates a torque that is this way, clockwise. So it's a negative torque, it's clockwise, okay? And as we go through, let me erase my trace here. As we go through, we slowly get some slipping or some rolling. We start building up some rolling. And at this point right here, 4.724 meters, we no longer get any slipping. We have a rolling without slipping velocity. So we can calculate our translational kinetic energy. We can calculate our rotational kinetic energy. Those have some sum. And we used heat too because we had the mass turn into friction. Now, here is the slip distance, 4.724. Okay. Suppose I change my radius to 1.5 meters. I make it a fair bit bigger. 4.724. Let's write that down. 4.724 was our slip distance. So mass equals 5 kilograms. We have mu equals 0.15. V0 equals 5 meters per second, and R equals 1.0 meters. We're dealing with a solid cylinder. Okay, so I equals 0.5 mr squared, and our slip distance was 4.724 meters. Let's verify that. Let's go back and verify that. Make sure I didn't remember wrong. 4.724 meters. That's our slip distance. Reset, erase trace. Let's suppose I make the radius now 0.4 meters. Is my slip distance going to go up, down, or stay the same?
It's gonna go down.
It's going to go down. So remember when we did this on the board, that the velocity became 2gh divided by 1 plus alpha if we're sliding down a plane. So the velocity didn't depend on the radius or the mass.
Oh, right.
You might even guess that the radius might not depend on the velocity, on the radius. The slip distance may not depend on the radius or the mass. Now let's see what our simulation tells us. Let's believe our simulation is correct. Okay, it makes more rotation. Orange is no slipping, blue is slipping, distance is 4.724. So it makes more rotation, but does not change the slip distance. Drive this all the way down to 0.1. Here, it made some full rotations, but here's my slip distance, 4.724. Let's go back to 1. Same slip distance. Note, this is talking the slip distance as the point of the center of mass. Okay, it's given the point of the center of mass. Let's reset this and run it again, and you'll see I'm gonna pause it right about there. See this? This is the point of the center of mass. We're almost at the point of no slip distance. Okay, that's the point of the center mass. If we reset it again and we go to 2 meters. Doesn't end up rotating very many revolutions before it gets rolling without slipping, but still the slip distance was 4.724 meters each and every case. Guess what? If we change the mass, same thing. We go back to 1, erase all the traces, reset this thing, and we run this again. We pause it, reset over to here, change the mass to 10 kilograms. That doesn't even change anything. You see, it's all identical. I change the mass. I reset it. I move the mass down here. Same thing. Okay? They're always the same. Now, if I increase the coefficient of friction, am I going to increase or decrease the slip distance?
Decrease.
Decrease. And that makes sense. So I'll go up to 0.3. I'll double it. Okay? If I increase the coefficient of friction, I've got a higher torque. I've got a fixed moment of inertia. I've got a higher torque. Now it's 2.362. Go back to 0.15. Now, if I increase the initial velocity, am I going to increase or decrease the slip distance?
Increase.
Increase. And here it stopped slipping off the chart. Okay, at 18.896 meters. So on this lab, you're going to do a few different things. You're going to look at the final, you're going to take a look at the force on object due to friction while slipping. Well, the force is the coefficient of friction times mg. Okay, you can calculate that. The force on object due to friction while slipping is the coefficient of friction times mg. The torque on the object while slipping is the force times the radius, whatever radius this is here. So here I have mu. Okay, I have mu mg. Here's mu. Here's m, and you know g. The torque is mgr. Here's the radius. The initial kinetic energy is 1/2 mv squared. You can calculate it. You can also get it off of here. This tells you the initial translational kinetic energy. We have the slip distance. You're going to determine that experimentally. You're going to look at the experiment. You're going to get the final velocity of the center of mass. It gives you all that. Run. Reset. Erase traces, run. Okay. Here is the initial velocity was right here, 5 meters per second. Here's your center of mass velocity, 3.33 meters per second. For example, in this, these are not the same initial conditions of the table. Okay, these initial conditions, you're going to use different coefficients here. Okay, a solid sphere. You can do them all for a solid sphere. 0.4. Okay. Things like a mass of 1. Radius of 1. Coefficient of friction, 0.05. Initial velocity, 2. Erase traces. Okay, So this is the first one. Force on object, mu mg. That's the force of object due to friction. Torque, mu mg times radius. Force times radius. Force times distance. Initial kinetic energy. Well, it gives it to you. It gives you 2 joules. Or you can calculate it. 1/2 mv squared. That's all it is. 1/2 mv center mass squared. It has no rotational.
Did you put the formulas for that up, up on top more?
Yeah, but you should know this by now. What's the formula for kinetic energy? Translational kinetic energy.
Ke equals 1/2 mv squared.
Correct. That should be in your head like this now. Okay? That you really want to have in your head right off the top. If I ask you what the translational kinetic energy. Now, starting today, you got rotational kinetic energy. 1/2 I omega squared. That should be in your head by end of day today. Okay? Because it's still 1/2 mv squared, but we're going to change m with I. You guys already had mass, and that in rotation, we talk about moment of inertia and velocity for omega. Linear velocity or translational velocity, angular velocity.
1/2 I omega squared.
1/2 I omega squared. Okay, so you're going to fill in. Now, I do give them to you up here. Okay, so you can calculate them. Okay, but it is also true that it's also true that this gives you the initial translational kinetic energy. The slip distance you're going to find experimentally. Slip distance was 1.999 meters. The final velocity of the center of mass, okay, that's this velocity. Rolling without slipping velocity is the velocity of the center mass. 1.429 meters per second on that one. You can write in 1.429. Okay, the final velocity of the center of mass. See that down here?
Okay.
See that down here?
Yep. Yep.
Okay, that's what this velocity is here. Final, the angular velocity. Now, nowhere on here does it give the angular velocity. This is the angular velocity after slipping. V center mass is equal to R omega. So omega is equal to V center mass over R. Okay, omega is V center mass over R. You guys should be able to get this. That is the angular velocity. The final translational kinetic energy, they give it to you experimentally, or you can calculate it. 1/2 m V center mass squared. Final rotational kinetic energy, 1/2 I omega squared. Now, I is 0.4 mr squared. You do have to put in the mr squared at that point. Okay, that's the rotational kinetic energy. The total kinetic energy, which is also, they give it to you here, okay, is the translational kinetic energy plus the rotational kinetic energy. And finally, how much energy is lost. Okay, thermal energy created. So the work goes into the change in kinetic energy. Okay, now we have 1.41 So roughly 0.59. It could be round off errors in these calculations. But your translational plus your rotational kinetic energy is equal to the thermal energy created is the work done. And that's the change in the kinetic energy. The change in the kinetic energy, this is the change in translational kinetic energy, and we can look at the work done on an object. Okay. Now, we can do work on an object by doing force times distance, which is F times D. That's the work done by friction on the object. In this case, our force is equal to mg, and D is our force is equal to mu mg.
Move the lab out the way.
If I want to do the work for the first one, my work was mu mg, and D was equal to 1.999 meters. Mu was 0.05. Mass was 1. G is 9.8. And work is equal to F times D. It's negative, of course, which our force was in the negative direction. Our D is in the positive direction, which is equal to minus 0.05 times 1 times 9.8 times 1.999. And that equals, grab our calculator, 0.05, 1 times 9.8 times 1.999 times, and we get 0.9795 using the force times distance calculation. But we were doing some rolling at the same time. So put a question mark. We're doing some rolling at the same time. Part of this time we were doing rolling. So we weren't always doing that work. So I can't simply use this, because this is not correct. This is slipping distance, not work done distance. And in fact, we can use our change in kinetic energy for the work done on the object, because we weren't doing work on the object the entire time. We weren't doing work on that object for that whole distance. This is the distance that the center of mass moved. So we can use our work energy theorem to get the work done. All right. So so you're going to spend some time on this. Now you have the last part of this lab, however, is a tad more challenging. You have to do the calculation in advance. So determine the coefficient of friction required to stop slipping and start rolling without slipping. So I'm going to assume you have a hollow sphere. So first assumption is hollow sphere. What is M equal to 4.0 kilograms and R equals 1.5 meters? Okay, now what's I equal to? We've shown this a couple of times. I have things like a solid sphere, a spherical shell.
Oh, that, oh, okay, that's what you're saying. So
This
this
is
is
the same as a spherical shell.
a
Your
hollow
simulation,
sphere?
which is the same as a spherical shell.
Oh, okay, so
Thin
it's
spherical shell. Remember, it's
2/3.
2/3 mr squared. So we have what I equals. We have V0, the center mass, is 6.4 meters per second. And omega 0 equals 0 meters per second. Calculate the coefficient of friction required to begin rolling without slipping in 7 meters. So mu k equals question mark for rolling in 7 meters. Okay. So how do we solve this problem?
Just plug everything into the eye.
Well, we can plug some things into I, but you know, we have to solve a few equations, right?
Yeah.
Okay, so what are some equations that we have to solve? What is our force of friction? Force of friction kinetic is equal to mu mg, right? So we have a ball here. Here's Fk. That's our free body diagram. Translational. We can write my sum of my forces, which is equal to minus Fk equals minus ma. Okay. We know acceleration is this way. So here I'm using my A as a positive value and my kinetic friction is to the left. So we've got that simple equation, right?
Sorry about that. Went to the restroom real quick. So
We just got F equals minus Fk. We got that simple equation.
okay.
Okay, now, so I just draw down okay. And Fk is mu k mg. Here's my radius r. Okay, so mu k mg equals ma, or a equals mu kg. Or if we want to write a vector is minus mu kg. Okay, So A is minus mu kg, because I have minus Fk here. So A is minus mu kg. We should have just written as Fk, and A is backwards. So A is in the negative direction. A is minus mu kg. Right? This is my positive X direction. This is my Y direction. So Fk minus Fk is equal to MA vector. A, I know, is going backwards. So minus mu mkg equals MA. And so A is equal to minus mu kg. Right?
Right.
Okay. So I've got A. Right now, V is equal to V0 minus mu kgt. Because V is equal to V0 plus AT. This is simply V is equal to V0 plus AT. And A is minus mu kg. Right? That's our translational. Rotational. Okay. Omega is equal to omega 0 plus alpha t. Alpha is also going to be negative. It's going to start spinning clockwise. Okay. Omega 0 is equal to 0. So omega is equal to alpha t. That's pretty simple, right?
Yes.
Okay. We've got another joiner. Hello there. Okay. So we've got V is equal to V0 plus AT. Okay. We know that V equals V0 minus mu k gt. We have omega is equal to alpha t. Okay. But that's the kinematic equation. We need an expression for R alpha. Well, torque is equal to I alpha. But torque is also equal to R cross F. Correct? And what is R cross F here? F is mu kgt. R crossing F is R mu kgt. And we need a minus sign. Okay. So A is slowing down. And again, here's places where you have to be careful because, we need to make sure that we get our signs right. So you have to look at your pictures. I'll usually go back and double check that everything makes sense. But right now, so we're going to go with our minus sign. So I'm going to double check that though. One has to be careful. Okay, so I now have from these ones here, I have, pull this up so I can get the top of my paper with some writing on it. I have V is equal to V0 minus mu kgt. Torque is equal to I alpha, and torque is equal to minus R mu kgt. So. Alpha is equal to torque over I, which is then equal to minus R U K G T divided by 2/3 M R squared. We in agreement so far?
Yes.
Which is then equal to alpha is equal to an MR squared here, I'm missing a mass somewhere. You guys let me get away with this. Mu K M GT. The new M was supposed to cancel out, and this is an M times M. Let's just write this out a little bit better, a little bit neater for you. Minus R mu K M GT. So alpha, which is equal to torque over I, is equal to minus R mu K M GT. My force is mu K M G. Okay. This should not be torque is minus R mu K M G. No T here yet. No T here. You guys are letting me get away with things. Minus R mu K M G. That's force mu K M G times distance in the negative direction. Okay, minus R mu K M G over 2/3 M R squared. Okay, my M is going to cancel. One of these is going to cancel. So alpha is equal to 3 mu K G over 2R. Okay. Now, omega is also equal to, omega then is equal to omega 0 plus alpha T. So omega, this was 0, is 3 mu K G T over 2R. Okay, so I have what omega equals. So I've got an expression for omega. This is omega final. That's when we have rolling without slipping. Okay. I also have V is equal to V0 minus mu KGT. Correct? Correct?
What? Yeah, I'm ready. Everything. Yeah, sorry about that.
Okay. Now, what else do I know? I've got an equation here. I've got an equation here. What else do I know? Rolling without slipping. So we don't know T. We don't know T, right? We have no idea what T is, but rolling without slipping condition. V equals omega R. But look what my final condition is when I have omega final. This is all what we're looking for, is that when V equals omega R, that's my omega final. So omega R is equal to 3/2 mu K G T. And that equals V. Or mu K G T equals 2/3 V. Now, why do you suppose I wrote that?
So you can plug it into omega final. No, into
I have
the,
two.
into the final velocity is equal to the initial
Right.
velocity minus.
I've got that. I can write that. So now I can put it here. So I can write V equal to V0 minus mu K G T is equal to V0 minus 2/3 V. UKGT, 2/3 V. So V equals V0 minus 2/3 V. Or 5/3 V equals V0. Or V equals 3/5 V0. So that seems like a pretty big deal to me. V equals 3/5 V0. Okay. Now where am I? Now I'm writing big. You can get this all on one page.
I have a tutoring appointment I have to go to at 12:45. I'll catch it on the video. Okay.
Okay,
Okay.
we'll be back. We'll be done in just a minute, but all right. Okay. So then I tell you. Now I have V. Remember, V squared equals kinematic equation of motion, V0 squared. So we're pulling a lot of things out of our toolbox, plus 2a x minus x0. A is equal to minus mu K G. Remember, we had that UKMG. Okay, remember, right? We had A. Well, MA is minus mu KMG, so A was minus mu KG.
Yeah, I remember that.
So V squared is equal to 3/5 V0 squared equals V0 squared minus 2 mu KG over x minus x0, or that's just delta x. And that's what we want to solve for mu k for delta x to be 7 meters. So let's combine our V0 squared. So I have 9/25 minus 1 V0 squared is equal to minus 2 mu KG delta x. Or we can do 1 minus 9/25 times V0 squared. All of that divided by 2g delta x equals mu k. And this is equal to 25 minus 9 over 25 v0 squared divided by 2g delta x. This is 16 v0 squared over 50g delta x equals mu k. The mu k is equal to 16. V0 was 6.4 squared over 50, 9.8, and 7.0 meters. Now, you have to remember how to do this and write it up. Okay. If I,
Is that a 6.4 squared times 16? Or for like when you're solving for mu k?
yeah.
Oh.
So this is how you go about solving for an equation of sliding without, with slipping to find the slip distance.
Wait, sorry, can you repeat that?
We're solving for the coefficient of friction such that something stops sliding. And you weren't here for the beginning, right?
No, I had internet issues connecting. I kept trying to connect and it kept kicking me out. It was just like trying to connect, and then it just would boot me out.
Okay, our lab here is we've got a condition where we've got slipping without, so we're launching something with an initial translational velocity along a rough surface.
Mhm.
There is a slipping distance. Okay, before it starts rolling. Okay,
Okay.
so the center mass, for instance, here was an initial velocity of 5 meters per second, a coefficient of friction of 0.21, a radius of 1, a mass of 1 for a thin spherical shell. Don't worry about the fact it shows a basketball. We chose a thin spherical shell,
Mhm.
okay, which is kind of a basketball. And it slipped 3.88 meters before it was fully rolling without slipping. Something rolling without slipping is like your car tires, or when that would be rolling without moving. So you have rolling and slipping. When your car tires are firmly attached to the pavement, they're rolling without slipping. Okay. If I took a bowling ball, a typical bowling ball, if you have ever gone bowling and you throw it,
Yeah.
now you're throwing it pretty much with just a translational velocity. Maybe you put some sideways spin on it, but you pretty much don't put any forward or backward spin on it. You might put some sideways spin on it, but you're not putting, so you're giving it an initial velocity forward, and it picks up its rolling because of friction between it and the floor. It's not immediately rolling, and it's not pure rolling. You have rolling and slipping happening.
Okay.
So you can see here that this was its slip distance. We already showed, and you can watch the video again, that if I increase the radius, I don't change the slip distance. The number of rotations it changes might change, but I don't change the slip distance. Here was still 3.88. Okay, if I just change the mass, I don't change the slip distance. If I change them both, I don't change it. 3.88. But if I change the coefficient of friction and increase it, well, now I'm slowing it down faster and I'm adding more torque. So I run this. And clearly, I reduce this slip distance. Now,
Okay.
1.432 by increasing friction.
So only changing the friction value will it change the slipping distance.
No, not quite. If I keep my velocity constant. But if I increase my initial velocity, so let's reset this again.
Okay.
I think I seem to have crashed it. Okay, so here I hit run. So here was 5.443 for a thin spherical shell, initial velocity 5, coefficient friction 0.15, radius 1.5, mass equals 2. Now we've already shown affecting the radius doesn't have anything. So I reset it, erase my chases. If I increase my velocity, yeah, the slipping distance is going to get longer. And sometimes a lot longer. Here it went to 16.14.
Yeah.
Okay, so my initial velocity is increased, the slipping distance is going to increase. That makes sense.
Mhm.
Okay, if I increase my coefficient of friction, my slipping distance is going to decrease. So initial velocity and coefficient of friction are what it depend on. The problem you're asked to do in exercise 2 is with 4 kilograms, 1.5 meters, which turned out they don't actually matter. They're going to give you any mass and any radius. And we start with initial translational velocity of 6.4 meters per second. So here's my 6.4. Okay. I have a hollow sphere. Well, hollow sphere is the same as a thin spherical shell. Okay.
Okay.
What coefficient is required to get it to stop in 7 meters? That's the calculation we went through, recalculated it. Now, for instance, if it's my coefficient of friction here is say 0.39, and I do run, well, it stops in much less than 7 meters. I asked you to find out what it takes to stop in 7 meters. That was the delta X that we put in there, okay?
Yeah.
Get the final equation. Now, I calculated out what it should be.
The 0.1911. Is that
Yeah.
the one you're referring to?
But you're not supposed to have noticed that. You need to calculate this out for yourself. Okay,
Okay.
now, and I want you to go back through and learn this. But notice I put in a number close, I get close to 7 meters. Your simulation will confirm your calculation. Okay, I went through and I did more of this than I wanted to do because it's a little bit of a challenging problem. I want you guys to get it, but I really want you to work backwards and make sure you understand all the steps we took in this, because we're comparing linear, translational, and we're doing something that I think is really, it is a challenge problem to deal with rolling and slipping. That is a bit of a challenge problem. I'm showing you how to do it, but I really want you to go through and understand this and then confirm that you can get that from the simulation. you'll find that there are a lot of simulations out there that if you're trying to figure out how to do a complex problem, sometimes you'll find out simulations that are only just a little bit simpler or a little bit more straightforward, but you figure out how to solve that one, you confirm it with a simulation, and then you get confidence in your solution for, say, a slightly more difficult problem. Okay, and
Got it.
that's all you got to do in this lab, but this calculation can be challenging. All right,
Yep. All right. Thank you for clarifying everything. Otherwise, I think, I don't know, I can't speak for everybody else, but I would be very confused doing the
look-
calculations.
that calculation is non-trivial, and it's not really explained how to do that in the book because it would be kind of a little bit of a bridging problem,
Mhm.
right? But we went through and we did it in detail here. Okay. Even with a couple of errors I made where I forgot even and added a T. But we finally got it straight. All right.
Yep. Thank you.
All right. Bye now.
Bye.